And we're back. And it's my pleasure to welcome Roy.
Hi.
Hi, Roy. How are you?
I'm fine. You? How's it going?
Very well so far. We've got very good talks and good feedback. Quite an atmosphere, quite a celebration of the 25 years of Java.
Yeah.
Of course. So where are you based now?
I'm in near Rotterdam in the Netherlands.
Okay.
Yeah. Working from home, obviously.
I think today we have similar weather or not. Is it cloudy or shiny?
I've got this.
I think your weather is better than mine because we have a lot of sun here in Yash, but today is so cloudy.
Yeah.
But not a problem because yeah, we've got all these interactions and all these talks to make the days better and better, I would say.
Yeah.
Right? Okay. One question.
Yes.
Just quick kick off the, the entire conversation. So, are we living in a quantum world?
What?
Are we living in a quantum world?
Well, yeah, the quantum effects are all around us. So yeah, I do believe when you go down deep enough, these quantum effects, yeah, they're there. So actually, the things we see in the world aren't really what they are. Like we see things behave like particles, but they're actually not. So yeah, we do live in a quantum world. The question if we will soon have quantum computers, well, I hope so. A lot of people are working on that. So,
why is it that you hope so?
Well,
many people are discussing also about threats and stuff, and you know, it's exposing ourselves to a totally new world.
Yeah, yeah, and that's the whole thing. It's a totally different way of thinking, of computing, and you can do things that we can't do on a classical computer. But more on that during the presentation, obviously.
Okay. Can you see the screen behind me?
I can, yeah.
Can you see what's in there?
I can see a tweet, but Bernard will.
Something.
Yeah, I've tweeted something similar. Yeah.
So
yeah.
What's in there? What's in there?
What's in where?
So I will get this closer then.
Yeah. Yeah, I know.
Okay. What's the story behind that? I wanted to just have a tiny conversation on that.
Yeah.
I read your blog article.
Yeah.
I enjoyed it.
This year, well, not the best year in the world, but hey.
Yeah, no worries about it. Okay, so how about today? What's gonna be your talk about?
Yeah, my talk is going to be about quantum computing. So I'll get into what you asked earlier. Why do we need quantum computers? I want to show how they work. I want to show a little bit about the math. I want people to get an idea on how do you use these quantum effects to do any meaningful computations. So, and what are the differences between computations done on a classical computer and on a quantum computer? So I'll dive into these topics, and perhaps people won't understand everything, and that's okay. But the main goal I want to give people is an idea on how these quantum computers work, what they do, what these effects are. Yeah, just
sounds very good to me. Sounds very good to me. So let's just go ahead. So you've got the floor, you can share screens, and yeah, good luck. And then we'll meet again during the before the break, right, to discuss a bit and have some questions and so on. Okay, thanks.
Will do. Can you see the slides?
Yes.
Awesome. So the presentation is called Untangling the Mysteries of Qubits. A little bit about myself. I'm Roy. I've done a couple of things. I work for a company named OpenValue, and we are based in Rotterdam, but there are also branches in Utrecht and in Germany as well, Austria. So there are a couple of OpenValue companies around the world. You can find me on Twitter and online if you've got any questions, or just ask after the presentation, obviously. So first, a small disclaimer, because quantum computing is hard. And so we have to take a couple of small shortcuts, mainly to keep it understandable, but also because, frankly, I don't know. A little bit of a warning, minds will be blown. So all the digital things around you, your computer, your phone, everything we do work on binary digits, bits. We all know this, and a bit can be a 0 or a 1. And what do we do with this? Well, your computer, for example, it just applies a lot of logic gates, where you have some 0s and 1s as input, and you have some 0s and 1s as output. And that's all we do. So the only thing your computer and this phone are doing, they're flipping bits. And you can do a lot of powerful things with this. We can do virtual conferences. But when you draw down, it's actually very simple. All we do is flip bits. Quantum computers, however, they work entirely different. So instead of having a bit that can be 0 or 1, it can be in between a 0 and a 1. One misconception is that people often think it can be 0, it can be 1, and it can be both at the same time. This is actually not true, because it always is some probability of it being 0 and some probability of it being 1. And these two probabilities combined are the qubit. So it can be 100% a 0, it can be 100% a 1, but it can also be 50-50 or 25%, 75%. It can be in every possible state. So like you asked before, why do we need quantum computers? Well, one example is prime factorization. So this is something very easy. We take two prime numbers and we multiply them together. I can, if you give me enough time, I can do this on paper. I can do this almost from the top of my head. The other way around, though, is very hard. Given a very big number and someone tells you there are two prime numbers in there calculated together, what are the prime numbers? This is something on a classical computer very hard to do. We are unable to do this. So if you would look at all the problems you can solve with a classical computer, that's the yellow part, and there are problems around that area that are very hard. So these are the P problems, which we can fix on a computer, which we know algorithms for, and NP, which can't be solved in polynomial time. And prime factorization is, as of today, something in the NP group. So this is a hard problem. And that's also why we use it for security online, because it's very hard to do these calculations. If you have a quantum computer, however, a new area is unlocked. And this is the quantum easy area. And prime factorization on a quantum computer can be done efficiently. So it doesn't solve all the problems we know in computing, but some of the problems, some specific areas, can only be done efficiently, as far as we know, on a quantum computer. So how does this all work? Well, a quantum computer works on quantum mechanical phenomena. And people always think that these phenomena are weird and you can't see these effects, but I want to prove that you actually can, and you can experiment with this. So what are these quantum effects? Well, if you look at water, you can touch water, you can feel water, you know what water is. If you drill down, you get to the molecule level. You've got two hydrogen atoms and one oxygen atom. So these things can be split up further. And if we drill down into, for example, an oxygen atom, you get something like 8 electrons, a couple of protons and neutrons. And if you drill down further in a proton, you can see this is also made up of parts, up quarks and down quarks. And there are all these small elements at this level, quantum elements, which behave in a strange way. So there are up quarks, down quarks, and photons and bosons. As far as we know, you can't really draw down further than this. And then you get these things. Some people call them particles, but they're actually not particles. And this was proven by the famous double slit experiment. So for example, if you were throwing tennis balls at this wall, which has 2 slots in it, then you would expect this pattern to appear. This is where the tennis balls hit. So if things would behave like particles, this is what you would expect. But if you do this, if you, instead of fire tennis balls, you would fire rays of light into, or photons into these very small slits, or electrons, you don't get this pattern, but you get this pattern. And this is a kind of an interference wavy pattern, and it seems to go places where you don't expect it to go. And it turns out the way it actually works is that these particles, they don't behave like particles. They behave like waves, and they interact with each other. So they are propagating forward, they go through both of these slits, and then they interact with each other, and then they end up on the wall. The weird thing is though, if we would look at one photon or one electron, and we would measure through which slot it's going, because it can't go through both at the same time. If we do a measurement, then suddenly it does behave like a particle, and it collapses and it decides I'm going through this slit, and then you get this this pattern like before. This is actually an experiment you could do at home if you have a laser pointer. You can watch some YouTube videos. They explain how to do this using a laser pointer and 2 small cuts. This is something you can see at home. Another example is polarization. So if you have a Polaroid camera or Polaroid sunglasses, what they do is they filter out some light. And you can do some experiments with this as well. So if you have 3 of these polarizing filters, then you can do something that really blew my mind the first time I did it. If you look at sunlight or any light from a heat source, for example, an incandescent bulb, these waves or these particles, the photons, they are moving in all different kinds of directions, either like this or like this, and it's completely random. So if we have this filter, and this filter is made up of blinds like this. If it's going like this, it will bump into the filter. If a photon is going like this, then it will just go through without any problems. So if we have this first filter, 0% of the light going like this will be blocked, will come through. 100% of the light going like this will go through. But if it's going at an angle like this, about 50% of the photons or 50% of the light makes it through. And as you can see here, I have 3 of these filters, and I just pointed the camera towards the sun, and I made some Lego holders. If I place the first filter, it blocks about 50% of the light. So the square is a little bit darker. And the camera is adjusting, so it isn't that obvious, but it's about 50%. The weird thing is that when we measure, we actually change the light. We change the direction in which it's going. So if it was going at an angle like this, and it was lucky enough, 50%, that it got through, at that point, it will be completely horizontal. So if we take this filter, we turn it 90 degrees, and we place it, a second filter, and we place it behind that first filter, now all the light going like this can pass, but all the light coming like this is blocked. Like I said, we just changed light. So after the first filter, everything's going like this. So we expect everything to be blocked. And it turns out if you do this, and you turn it, this is actually what happens. All the light gets blocked. You cannot see anything. The thing that really blew my mind is when I added a third filter to this. So first, the calculations, after the first filter, 50% of the light is coming through, and it's now going like this. After the second filter, which blocks this light, which only leaves this light and blocks this light, you get complete darkness. If we add a third filter and it's on this axis, then something weird happens. As you can see, if you put it in the middle, mind's blown. Suddenly light comes through again. So in my head, this doesn't compute. If you have two filters, you are blocking everything. It doesn't matter what you do in between. There's no way suddenly light comes through. And it's just weird if you have this material in your hand and you do the experiment. It's weird. But this proves we are actually changing light, because if you would look at the calculation again, after the first time, light is completely polarized like this. If we do it now through the second filter, there's still light coming through. And then the third filter, there is still light coming through, because you only eliminate half of the light at each step. You can even add more filters to this, like 17 filters in the middle, then almost all the light gets through. So this is very weird. And this is something you can do at home. Just order some polarizing filters. There are a couple of euros or something on Amazon, and you can play around, show your kids. Yeah. So what is actually inside one of these quantum computers I was talking about? It can be based on photon polarization. You can do calculations with this. It could be based on the spin of an electron or of other particles, nuclear spin. There's something called a Josephson junction, which is a small electronic circuit that behaves quantum weird. So this is obviously a popular choice for people experimenting with quantum computers, because it's easy to interface these electronical junctions with other parts of computers. There are bigger molecules that behave like quantum, in quantum weird ways, and these are called quantum dots. You can actually buy quantum dot televisions at the moment, where these small particles emit different wavelengths of light. They're not the best TVs, I think, but it's just cool that these use quantum effects to actually display something. Turns out, though, even the small LCD displays you used to have on calculators and stuff, these actually use the polarization of light to display. It's very cool to read up on how those things work, but yeah. So why don't we have working quantum computers? Well, there are a couple of problems with quantum computers, and these you have to manipulate these objects at a very tiny scale. And if something is hot, it's moving around. Like if an atom is hot, it's constantly moving around. And it's impossible to manipulate these things. So to do this, we need to cool everything down to near the absolute zero, and that's the point where things stabilize, and that's when we can manipulate these small particles. So we have to freeze everything. That's why quantum computers often look like this. They're hung from ceilings, and they look like fancy chandeliers, but that's all due to the cooling. So you have to isolate things and cool things, so that's why they look that weird. So it's all very complicated, but let's just build a quantum computer, or rather, let's simulate one in Java. To understand how to manipulate a qubit, I need to ask my friend, and my friend is Mr. Qubit. He's here, and he's very helpful in explaining some of the operations you can do on a qubit. So imagine having a qubit is much like a skippyball or a sphere. This is called the block sphere. And this pointy thingy is, points to the probability. So if it's oriented like this, this direction means it's a 0. If it's oriented like this direction means it's a 1. So if you would measure this qubit and it's oriented like this, it will always return a 0. If it's oriented like this, it will always return a 1. If it's oriented like this and you do a measurement, it will instantly snap to 0, or it will instantly snap to 1. And after that, you've changed the qubit, you've changed the state, it's now in a different position. So this qubit, this skippyball works great as a qubit analog. To describe the state of this qubit, it's very simple. We have two probabilities. So we have a certain probability of it being a 0, and we have a certain probability of it being a 1. If it's like this, it has a high probability of becoming 0, because that's close. And all the way to here, that's a 1, so that's a very low probability. And there's some that involve that these probabilities are shared equally. So if we would draw this, if we would code this in Java, we would need just two complex numbers, and they will represent the probability of it being a 0 or probability of it being 1. And if we initialize these complex numbers with 1 and 0, we've just created a qubit that points like this, with all probability of it when measured becoming a 0. Einstein says God does not play dice with the universe. He was a very quantum skeptic dude. He didn't believe in most of the theories around quantum elements and quantum effects. And he always had the feeling that things shouldn't be random. But if we want to make a measurement of our complex system, the first thing we do is use random. Then we just loop over the states and look at the real part, and then we return our measurement. So it's very easy to, when you have a single qubit or you have a system of qubits, actually do a measurement. You just pick a number between 0 and 1, and you look at, and you go through all the qubit real values until you've reached that point. So in classical computers, we flip bits using logic gates. What do we do in a quantum computer? How do we manipulate these qubits? We do this using rotations, but also using matrix operations. These matrix operations, they describe how we rotate our qubit. So, for example, Pauli was a mathematician. He not only came up with one gate, he invented 3 different gates. So the first one is the X gate, and the X line goes through here. So what does this gate do? Right now our qubit is completely, all the probabilities point to it being 0. If we apply this X gate, this happens. Now it becomes completely a 1. And if we apply it again, this happens. So that there are 2 things we can note here. One, this is actually a NOT gate. So if it's a 0, we turn it into a 1. And then we turn it into 0 again. But also, if we apply the operation 2 times, we end up with the same thing as we started with. And this is true for all the operations in a quantum computer. So what are these other 2 gates? Well, there's this and this. And there's also rotating to this and to this. As you can see, the first rotation turns a 0 into a 1, then back into a 0. The second rotation from a 0 to a 1 to a 0 again. But the third one, it doesn't change the probabilities. It does change something, but it doesn't change the outcome. So it's always a 0 if we measure it. It's always a 0 as we measure it. But there's something different because you can no longer see his face. His face is now hidden. So we can encode more information into a qubit than just it being some value of 0 and some value of 1. There are other elements in there as well. And that's why we need those complex numbers to describe the state of the system. If we would want to write code, we can just make, you can use Commons map. We make a system with a single qubit, a probability of it being 0 and a probability of it being 1. And then we apply this matrix with complex 0s and complex 1s. And if we apply it, the qubit will now be flipped. So if we initialize it like this, and we apply the X gate, and we measure it, we will always get a 1 instead of a 0. So this shows that the way to manipulate these things can be mathematically done as matrix operations. And it's actually very easy to simulate a quantum computer. The problem is scaling, but we'll get to that. Like I said, all these quantum gates, they are unitary, which means that if you apply them one time and you apply them again, you go back to the original state. This has to be true, except for measurements. If it's like this and you measure and it pops to this, you've changed the system. You can no longer undo this. You can no longer look at what the state was before, because the state now becomes entirely a 0. There are other gates. For example, HADAMARD, he was a real badass. He didn't take this axis or this axis. He envisioned an axis that's running from this point, like a unicorn, to the bottom. And if you would rotate around this axis, this happens. So the state of the system now, first it was 0, then we apply it, then it becomes this, and if we apply it again, it's 0 again. But if it's like this, that's called a superposition. Like this thing is in the middle, and once you measure it, it can go either up or down. But this system, after applying a Hadamard operation, is in a superposition of 0 and 1. It's somewhere in between. Actually, it's right in the middle, in between. So if we would apply this matrix operation, the same code as before, I've just changed the field in this matrix, and then we do the measurement we did before. You get 50% of the time a 0, and 50% of the time you get a 1. So these matrices are very simple to implement, but they behave like a quantum computer should behave. This is also where Schrödinger's cat comes from. So the story about Schrödinger's cat is you take a box, and this box is you can't hear anything from inside the box, you can't see anything about the box. It's completely sealed and it's very thick. And now you put a cat in there, you put a decaying atom in there, and you put the poison in there. And once the atom decays, which can be now or in 2 days, you don't know, the poison is activated and the cat dies, sadly. And Schrödinger was joking. So if we don't know the state of this system, is the cat alive, dead, or is it both at the same time? And obviously the cat can be both at the same time, but this is an alibi for these complex systems that have these weird effects in it. And it turns out you can have these superpositions where when you do a measurement, it suddenly flips. And this still pisses a lot of people off because it does not make sense, but it's just how works. Yeah. There are also operations you can do on multiple qubits. So if you look at the white square there, these lines represent 2 different qubits, which are initialized at 0. And then we have an operation with the black dot and the circle below it. That's a controlled operation. So the first one is the control point, and the second is where the operation is taking place. And this is a controlled knot. So if the first one is measured to be a 0, the second bit, nothing happens. If the first one is measured to be a 1, the second bit is flipped. And as you can see in the matrix, the small poly X flip operation, the knot operation, is hidden inside this matrix. Now we can get to something really weird, and that's the Bell state. If we first do a Hadamard operation, so we do the first one, we do this, we turn it into a superposition. It can be either up or down. And now we go through this controlled knot on the second qubit. So the first qubit goes like this, and then we do a measurement and it jumps to 1 or it jumps to 0. On the second qubit, if the first one is measured to be a 0, nothing happens. If the first one is measured to be a 1, it instantly flips here as well. Because these 2 states can no longer be seen as 2 different states. They are intertwined, they are entangled. This is quantum entanglement. So if we write the code again and we test it 1,000 times. So on this first gate, we do a Hadamard gate, which does this. And then we do a C0 gate. And we measure the outcome, it's either 0, 0 or 1, 1. And it's never these things in between. And this is very weird, this quantum entanglement. Because if you would take these 2 entangled particles, you would send one to Mars and one on Earth. You would measure the one on Earth, then you instantly know the value of the one on Mars. And this can be used to encrypt data, to send it somewhere, and you'll be the only one to decode the message, as well as the other holder of the particles. And this is very weird. And Einstein, for example, he didn't believe this could possibly be true. He called it spooky action at a distance, or spunkhafte Fernwirkung. He did not believe these particles would make up their mind at that instant, communicate with each other over enormous distances instantly, He just felt like there had to be something in the particle already when it was created that would change the outcome eventually. And for a long time, people agreed with him because, one, he's Einstein, and second, it just makes sense. There is some hidden variable there, and these particles don't make up their minds when they're measured. It happens before that. Until that guy named Bell envisioned a test that actually proves that this is not the case. So the Bell test works as follows. When you create a particle out of pure energy, then you can create particles. So from pure energy, you can create two particles. And when these two particles are created at the same time, they have completely opposite spin. So it's not like they're actually spinning around, but you can envision them spinning different directions. So we create these particles with complete opposite spin. If we would measure these particles along the same axis, they will always disagree with each other. So if this one is measured down, this one will be up. If this one is measured like this, the other one will point like opposite to each other. Now Bell said, instead of having just one detector, what if we place 3 detectors at different angles? Well, if we both measure the same among the same axis, like I said, they will always disagree. So if we measure like this, one will be up, the other will be down. And if we measure like this, one will be up, the other will be down. Like they will always disagree with each other. But Bell said, what if we measure random angles? So we don't measure along the same axis because we know what happens when we pick the same axis, they disagree with each other. What if we have the other axis? His first case was, there is a predetermined plan. So let's make a predetermined plan. Let's just say when we measure like this, the first one says it's going that way. Then instantly the other will say, I'm going that way. The other plan is, when it's measured like this, it's going that way. So the other one is going that way. So they always disagree with each other. This is one of the random plans it could have. If we look at all the possible measurements that you can do with this plan, that are these measurements, these are all the combinations. And now we can write down if they disagree or they don't agree. If we measure along the same axis, they will always disagree. So this is disagreement. If we take this direction and this direction, they both point outwards. So they agree with each other. In this case, this angle and this angle, they disagree with each other. So you can write down this table, and it turns out 5 out of 9 times they will disagree with each other. And this is to be expected. There are 2 other cases where you make a predetermined plan. And if you make all these plans for 3 directions, all possible plans, 6 of them will get to 55.6% disagreeable. 2 of the plans always disagree. Doesn't matter which option you choose, they all disagree. So if one is pointing all outwards, the other is all inwards, then they always disagree with each other. So if we would do this test, we create these particles with different spin and we measure them among random axes, we want them to disagree at least 55% of the time. The second case is, once we measure a particle like this, the other particle instantly flips to the other side. So by measuring it, it actually instantly flips to the other side. This is what we expect in a quantum world. So if we measure this axis, it will be down. After this particle is being down and we measure the second particle, there are 3 options left. The chance of it being up is obviously 0 because it will always disagree. But because it's already pointing down, there's a 75% chance of it going to that direction from here to there or from here to there. So if you would add up all these possibilities, it will be about 50-50. So random measurements in a quantum world, you would expect a 50-50 disagree rate. And it turns out if you do these actual experiments, you'll end up with 50%. So this means there's no predetermined plan. These particles decide at the moment you measure them what the measurement will be like. And this experiment has been done over and over, and each time scientists find the same outcome. We've talked about what quantum computers do, what these quantum effects are, but how, as a programmer, can you use these weird rotations of a skippyball to do actual computations? Let's dive into that. The first one I want to talk about is Grover's algorithm. Imagine you have a large set of unordered data. So, for example, a deck of cards that has been shuffled. A shuffled deck of cards. And we want to find the ace of diamonds. If you do this on a classical computer, the only way to do this is to just go card by card by card by card until you find the ace of diamonds. Because it's unordered, there's no order in this data. We just have to go through the list, and once we find it, we stop. This is the only thing I can imagine doing on a classical computer, and scientists tend to agree with me. It would be very powerful, though, if we could have an enormous set of unordered data and actually find this one or multiple entries faster. Turns out, on a quantum computer, you can do this. So first we encode all these cards into our quantum system, and we give everything a superposition so they have equal probability of it popping up. So all these cards have equal probability. If we do a measurement now, it can be any card with equal probability. Next, we define an oracle function. And I'm not talking about that oracle, but a function that returns 0 for all the other cards and a 1 for the card that we are actually looking for. There is one caveat. We can't just apply this function to everything, because every function we make in a quantum computer has to be reversible when applied again. So we can't just put every probability to 0 and our probability to 1, because there's no way to undo this. Nobody knew what the system looked like before doing this transformation. What we can do, however, is use this weird property where we don't change the probability of this system, but we rotate something else. For example, we rotate this face around to change other parts of the probability without changing the outcome. And in this case, for our card, we just flip the probability. So we don't change the probability, we flip the probability. And as you can see, this is easily reversed because you can just flip it back. The second thing we do is that we take an average probability of all the qubits and we flip along that axis. So if we would do that right now, we would take the average and then we flip along this axis. This happens. And right now we did change the probability of 7 according to the other outcomes. So if you measure now, there's a slightly higher chance of getting number 7 or the ace of diamonds than all the other cards. But it's not that clear yet. But thankfully, we can just do the same operation again and again and again. And if you would do the same operation again and again and again, you'll end up with something like this. And if you have something like this and you do a measurement, there's almost certain that you'll get the number you're looking for. And it turns out this can be done in a quantum computer faster than just iterating all the numbers, because the speed is actually the square root of n instead of n steps. And this is just one small way, one building block of how you could use these effects to make a program run faster. Often you'll see that Grover's algorithm is a small building block in another quantum algorithm or a quantum program. The second one is the most requested one, that is Shor's algorithm. So we've just looked at prime factorization. If you have this very big prime number and you want to find the prime numbers that it's made up of, what do you do on a classical computer? Well, you just try every prime number. You try dividing by 2, dividing by 3, dividing by 5, until you find the number that actually divides the number. This is very slow, obviously, but it's still the best thing we can do on a classical computer. Shor's algorithm is a little bit different, though, so, but very easy to understand. Let's look at some examples. Step 1 is you pick a random number between 0 and the number you want to factor. So in this, and then you check if it's a prime factor. For example, if you want to factor out some million-digit number, you pick a random factor and it turns out that it is the factor you're looking for, you need to stop because you've hit the jackpot, you can stop. In this case, I'm using 15 as our big number we want to factor, and the random number we pick is 7. This doesn't look like a big number, but a couple of years ago, this was the biggest number actually factored by a quantum computer. So this kind of shows the state we are currently in. What we now do is we find a period R for a mod n. This sounds very complicated, but if you see an example, it's very easy. So we take our random number 7 to the power of 1, mod 15, squared, cubed, etc., etc., etc. And you'll see a pattern start to appear. It repeats after 4. So this means that the period of this random number and the number we're looking for has a period of 4. And this period can be as small as 1, but it can also be as big as the number itself. Now, the final step we need to do, if R is odd or if this equation equals 0, then we have to start over. We've picked the wrong random number. Let's try again and do this until it works. This happens sometimes. If you're unlucky, then you just pick another random number and until it works. If it's not odd and it doesn't fall into that odd trap, then we can just use the greatest common divider to calculate two numbers, P and Q. And if we would do that using our random number 7 and the period 4, then you get 3 and 5. And 3 and 5 are the prime factors of 15. 3 times 5 is 15. I can do that. Yeah, so that's kind of how Shor's algorithm works. And it looks much faster and much better than just trying to divide by each prime number, which we are currently doing in our, if you want to break like HTTPS. So what's the problem here? Pick a number, find the period, check, and calculate the prime factors. The problem is finding the period, because this table is basically the same problem as we had before, because this could require as much computation as n itself. So it would still take a lot of steps to calculate this period. Turns out on a quantum computer, you can do this much faster if you use the quantum Fourier transformation. So first we encode all these qubits and we entangle them using the HADAMARD operation. Then we turn it like this, from 0 to 50-50. So all of these particles can be entangled. And then we put in these numbers. And instead of calculating each number, we can just put in the calculation and we can do this operation on all qubits at the same time. This doesn't help us yet, because if we would now do a measurement, we would just get a random value from this sequence. And we don't want a random value from the sequence. We want to know how often this sequence repeats. To do this, we need to transform our signal, like all the numbers we get, into the frequency domain. So imagine we do these calculations for 128 times. Then you get this kind of graph. And you can see it repeats, but it tells you nothing about the amount of numbers it uses before it repeats. If you do the Fourier transformation or a quantum Fourier transformation, you get 4 distinct peaks. And if we would do a measurement right now, for example, it ends up here, then you can see that you get some information, but it's not enough. So by just having a single number, you don't know how many peaks there are. But if you repeat this for a couple of times, so a second measurement and a third measurement, and a fourth measurement and a fifth measurement, then something weird starts to happen. So after the first measurement, which was somewhere in the middle, it could be that we have 2 peaks, that it's 1/2. It could be that we landed on the second peak of 4 peaks, but it could also be the 4th peak of 8 peaks. It could also be the 8th peak of 16 peaks. But it gives some information about how many peaks there are. But after the second, which is about 3/3, then we can kind of see, okay, then it's not likely that we have just a single peak in the middle. So one over 2 is out of the question, but 3/3 is still an option. And if we just continue that, and the final measurement was a 0, these are worthless. You don't have to, these give you no information about the amount of peaks there are. But if you will repeat this for just a couple of times, you get a pretty good idea about the fractions that actually make up the period. So how many peaks there are. So in this case, it's most likely that we have 4 peaks. So we can just plug in R is 4, and then we calculate P and Q and check if those are the prime factors. So how fast is this algorithm compared to the classical way of just checking? The best way of just checking all the numbers at the moment is the general number field sieve, and it has a big O notation of this value, which says nothing to me. And if you would look at the speed of Shor's algorithm, someone on Reddit said, someone on Stack Overflow mentioned it's probably 72 log n squared. Fun fact though, the person replying that the best estimate might be this is actually Peter Shor himself. He is on Stack Overflow answering questions about this algorithm. Funny. But if you will plot this in a graph, you will see that just a number which is a couple of bits long, the general number field sieve will quickly grow into a runtime of 1 billion years. And Shor's algorithm is the lower line. It's based on, in this case, 1 gigahertz qubit. You'll see that it has a very different path. It doesn't grow exponentially. So this proves that these quantum algorithms are just way more efficient at solving some of our problems. And actually, if you would implement Shor's algorithm on a real quantum computer, you would probably only do the period finding on a quantum computer. The other stuff is much faster to do on a regular computer. So it will probably be some offloading machine where you offload some of the computations to the quantum computer and you get back the results. It's always a combination. So if these quantum computers are being made with enough qubits, actually the current cryptography will be broken. Like we can no longer use most of our keys because they are based on prime factorization problems. But luckily there are some answers for us waiting, because there are lattice-based encryptions, multivariate equation encryptions. You could use hash-based cryptography or codes, and there's also the super singular elliptic curves. Those haven't found, those ways of encryption don't have a BQB quantum easy way of solving them. So it would be actually good to already think about encrypting stuff using using these algorithms, because maybe we don't have quantum computers right now, but we can log everything right now. And maybe we have quantum computers in 5 years or 10 years. If you just log all the encrypted information, and then we suddenly have a very cheap way to read it, all your secrets are instantly thrown on the street. So if I was a bank, for example, I would already be looking at these other ways of cryptography to make sure that in a couple of years, people suddenly can read everything I'm doing right now online. So that's one of the takeaways of this talk, hopefully. If you want to learn more about quantum computing, you can go to IBM's website. IBM has a very cool interactive simulator. They also allow you to run your own quantum programs in the cloud on an actual quantum computer. So they have quantum computers, and they keep making these quantum computers better, adding computers with more qubits. But you can use real quantum computers and actually get real effects there. That's very cool. The Quirk is a very small simulator where you can try quantum programs and see how they work. Scott Aronson has a blog about quantum computing and about these quantum effects. Some of it is very deep for me. He did help me with some questions about this presentation, which I really thank him for. And all the code I showed of my own very silly matrix operation quantum simulator is on GitHub, and you can find it here. And that kind of sums it up. Are there questions?
First of all, congrats! Very, very well done. Yeah, so the audience says it was a very good talk, a very good presentation. It explained very well the concepts.
Thank
First
you.
time when I really understand what this qubit really means and stuff like that. And then we've got two questions in particular. The first one is related to, okay, the future is bright, for sure. There's a lot of potential in quantum and so on. Yep. How about threats?
How about threats? The thing is, when you do computations on a quantum computer, every operation you do affects the entire system. So there is no concept like threats on a quantum computer, because every step you do, it changes everything in the quantum computer. Every outcome is being changed. So it's not that easy to think about threats in these contexts. So,
all right, we've got Jamie on the line. Hi, Jamie.
Hello.
Bear with us. We're going to have a short break immediately after we finish the conversation with Roy, and then we'll. Okay. Good. Okay. How about cybersecurity in the quantum space?
Yeah, so I quickly, there are two ways to think about security using these quantum effects. The first is, if you have these quantum computers, you lose a lot of prime factorization becomes easy, so it's very hard to, it suddenly becomes very easy to break most of the existing cryptography. That's a risk. I would suggest moving towards elliptic curves just to be sure in the future that people don't instantly read what you've been doing online right now, because all of that will be out of the open once we have a big enough quantum computer. The second thing to think about is, can we use these quantum effects to encrypt data, or to make sure, for example, conversations can be listened into? And this is also an area of research that's being done, because you can use these, if these entangled particles are being read, it instantly changes the outcome. So you can safely transmit data, or, well, safely, at least you can see if people tampered with the message. This is also an area of research, which I don't know a lot about.
All right, thank you. And the last one was about any notable breakthroughs in the algorithms, in this area?
Well, not in the algorithm itself, but the main breakthroughs will have to come from actually having physical quantum computers that do this stuff. Like I said, it's very easy to simulate quantum computers up to a certain point, because for each qubit you add, you double the amount of state it can have. So having a simulator for 4 qubits is pretty easy, but if you add 10 more qubits, then it becomes impossible to simulate this on a classical computer. So the hardware really needs to step up and have, there are two problems with the hardware. First, it's very hard to scale and actually have more qubits. The second problem is that we can only use these qubits for a couple of operations, and then they just fall apart. They no longer function like they should be. So there are two ways that we need to improve these systems. That is having more qubits, but also having more stable qubits on which we can do more compilations.
All right, and the last one, I promise. Who are the biggest players, technology players, at the moment in the quantum computing?
Well, there are a couple of companies making quantum computers and experimenting with them, and that's a good leeway. IBM is one of the leading companies. Actually, they're doing a lot of research, and like I said, they've got this quantum computer online which you can test. But all the big companies, Google and Amazon, they're all working on their own quantum computers, and they're trying to find that thing that will bring it to the next level.
Yeah, so people say that is the next supremacy that many giants are looking at.
Yeah.
Right. Roy, it's been a pleasure.
Yes.
We're looking forward, well, to the next code camps, and hope to have you back again.